Okay, so now that we've talked about elimination, let's go ahead and introduce the idea of using matrices. A matrix is it's simply just a way to organize data in a clear and concise way without having to worry about having x and y and z and all that included with your coefficients. Really, the important thing when you're solving a system of equations are the coefficients, and knowing if that coefficient is on one variable or another. And that's what a matrix allows us to do. We can cut to the heart of the problem without having to have all this extra information. So let's consider the same system of equations that we just found a solution for. And I've rewritten the system here for reference. Let's go ahead and create an augmented matrix for this system. So what that means is we're going to assign to each column a single variable. And so every row is going to represent the equation from the system. So the first row would be equation 1, the second row would be equation 2, and so on. So let's go ahead and define the first column to be representing the coefficients for the x variables, the second column the y's, and the third column the z's. Now, you don't have to label your columns, and typically we do alphabetical or numerical order. That's sort of a good standard to use. So let's start with the first equation. If I read the first equation from left to right, I can see that I have 1x, 1y, and 2 z's. So I have 1x, 1y, 2 z's, and then I also need to include that constraint, the 12. So this is what makes this an augmented matrix, because we are going to include everything on the right-hand side of the equals sign, and we'll indicate that by a vertical bar. Now let's go ahead and look at the second equation. So in the second equation, we have 2 x's, 3 y's, a -1 z, and our constraint is -2. So we're representing the coefficients and the constant. And finally, let's look at the third equation. We have -3 x's, +4 y's, a +1 z, and a -8 for our constraint. So we enclose all of this in a big bracket, and that would be what's called an augmented matrix. Now sometimes we may be interested in just the coefficients, and if that's the case, then we focus on what's called the coefficient matrix, which would just be a matrix that is only the x, y, z columns, just the part that concerns the coefficients from our variables. So augmented also includes the constraints. A coefficient matrix is just the part that has the coefficients from the variables. Now, that means in this case, our coefficient matrix would be 1, 2, -3, 1, 3, 4, 2, -1, +1. Notice that the two matrices, the augmented matrix and the coefficient matrix, they are similar but they're different. These two matrices are not the same because they are not the same size. So even though most of their entries are the same, they're not the same size, so we cannot say these two matrices are equal to each other. The size of a matrix is given as a product. We write it as the number of rows by the number of columns. So if we look at this coefficient matrix, we have 3 rows, and we also have 3 columns. So this matrix would have size 3 by 3. The augmented matrix that we had before, this also had 3 rows, but the augmented matrix includes the constraint, so it has 4 columns. So this would be of size 3 rows by 4 columns. Whenever we're referring to size or location for a matrix, we will always use rows by columns in order to indicate size or location. Any item that is inside of a matrix is called an element, and we can talk about the location of an element as a coordinate, row by column. So for example, this 4 is at location, it's in row 3, so in position row 3, column 2, there is a 4. If we wanted to talk about, say, this -1, this -1 is in position row 2, column 3. Okay. So 2, 3, and 3, 2 are different positions, so the order does matter. We will always use rows first and then columns. Alright, that's it for now. Let me know if you've got questions.